All right, welcome to the Explainer. Today, we are diving deep, and I mean really deep, into the very heart of matter itself. We're going to unpack the atom, the fundamental building block of, well, literally everything around us.
I mean, have you ever just stopped and looked around and wondered, what is all this stuff actually made of? The chair you're sitting on, the air you're breathing, your own body. What is it at the most basic fundamental level? Well, the short answer is atoms, but the long answer, the story of what an atom actually is way more interesting, because our picture of it has changed so dramatically over time. So we're going to follow that journey, right, from this super simple idea of a solid sphere to, well, to a bizarre and beautiful cloud of pure probability. Trust me, this isn't just some boring history lesson. This is the story of how we figured out the fundamental rules that run the entire universe. Okay, so let's jump back in time to the early 1800s. This is where we get the first truly scientific theory of the atom. It was a pretty wild idea back then, and it all started with a really simple, elegant picture. So this guy, John Dalton, he comes along and says, hey, what if everything is just made of these tiny, solid billiard balls? He called them atoms. He figured they were indivisible, indestructible, and that each element, like gold or oxygen or iron, had its own special kind of billiard ball. And chemical reactions, that's just the billiard balls rearranging themselves into new patterns. It was a brilliant model, and it actually explained a ton about chemistry at the time. But, as great as that theory was, there was a problem. As our tools got better and scientists started poking and prodding at matter in new ways, they started seeing clues that this supposedly indivisible sphere could actually be cracked open. And this is where things get really interesting. This next chapter in our story is all about discovering the pieces inside the atom, the subatomic particles, and finding them would completely change the game. And the very first piece they pulled out, the electron. Using this cool device called a cathode ray tube, a physicist named J.J. Thomson discovered these incredibly tiny, negatively charged particles. And just their existence proved that Dalton's billiard ball couldn't be right. Atoms weren't solid. They had smaller, charged parts whizzing around inside them. Okay, so you found these negative little bits. How do you fit them into the atom? Well, Thomson came up with what we now call the plum pudding model. Just imagine a big ball of positively charged, pudding. And scattered all through it are the tiny negative electrons, like plums. Yeah, it's a weird dessert, but it made sense at the time because it explained why atoms are usually electrically neutral. But, that just leads to the next big question, right? If the negative electrons are like these little plums, is the positive charge really just a diffuse, formless pudding? Or was it hiding somewhere, concentrated? And that question led to one of the most shocking, game-changing experiments in the history of physics. Seriously. This one threw everything for a loop and completely junked the plum pudding model for good. So, Ernest Rutherford, who was actually one of Thomson's students, set up this experiment where he fired these tiny positive particles, alpha particles, at a ridiculously thin sheet of gold foil. He totally expected them to just zip right through, and, most of them did. But, and this is the crazy part, some of them were deflected, and a tiny, tiny fraction actually bounced straight back. Rutherford famously said it was like you'd fired a 15-inch cannonball at a piece of tissue paper and it came back and hit you. This result was just stunning. It could only mean one thing. The plum pudding idea was dead wrong. For a particle to bounce back like that, it must have hit something incredibly small, incredibly dense, and positively charged. All that positive pudding had to be concentrated in a tiny core, the nucleus. And the craziest part? The fact that most of those particles just sailed right on through meant one absolutely mind-blowing thing. The atom is mostly nothing. Empty space. So what's the new picture? Rutherford gives us this nuclear model. You've got a tiny, dense, positive nucleus right in the middle, and the little negative electrons are orbiting it. Kind of like planets zipping around the sun. It's a cool image, right? Very intuitive. But there was one, giant, fatal problem. According to the laws of physics, as they knew them, an orbiting electron should be giving off energy constantly. And if it's losing energy, it should slow down and spiral right into the nucleus in less than a second. Boom! If this model were true, atoms couldn't exist. Nothing could exist. So something was still very, very wrong with the picture. So to fix this atom-destroying problem, science had to basically break all the old rules. This is where we step away from the world we know and enter the bizarre, wonderful, and, frankly, weird world of quantum mechanics. And the first guy to really tackle this was Niels Bohr. He came up with a radical idea. He said, what if electrons can't just orbit anywhere they want? What if they're stuck in specific energy levels, or shells? They can jump between these shells, sure, but they can't exist in the space in between. And just like that, he solved the death spiral problem. But even that wasn't the full story. Modern quantum mechanics took it to a whole new level of weird. Forget the idea of a little planet on a neat little path. That's gone. The modern view, as you see here, is so much stranger. The electron isn't a point at all. It's more like a cloud of possibility. Our source material uses a perfect analogy. It's like a swarm of mosquitoes. You can't point to any one mosquito at any given time, but you know the general area where the swarm is. That's the electron. And there's a fundamental reason for this fuzziness. It's a rule baked into the fabric of the universe, called Heisenberg's uncertainty principle. It basically says you can know where an electron is, or you can know where it's going, but you can never ever know both perfectly at the same time. The more you know about one, the less you know about the other. It's not a limit of our tools, it's just the way reality works. And these fuzzy regions of probability, these mosquito swarms, are what scientists call orbitals. And please, let's get this straight because it's super important. An orbital is not an orbit. It is not a racetrack the electron is running on. It's the electron's house, a 3D neighborhood where it's most likely to be hanging out. So why should we care about all this weird quantum stuff, these fuzzy clouds and uncertainty? Because this isn't just abstract physics. This is the rule book for everything. This is the why behind all of chemistry, why things burn, why they rust, why they stick together. It all comes down to how electrons arrange themselves in these orbitals. Think about it like this. Every single electron in an atom has its own unique address, and that address is made up of 4 quantum numbers. The principal number, n, is like the state it lives in, its main energy shell. The azimuthal number, L, is like the city. It tells you the shape of its orbital. The magnetic number, ml, is the street address, the orbital's orientation in space. And finally, spin, ms, is the house number. It can be up or down. It's a perfect system, and no 2 electrons in the same atom can have the exact same address. So what do atoms do with all these perfectly addressed electrons? Well, they do what anyone with valuable stuff does. They trade them, they share them, they bond. Sometimes, in what's called an ionic bond, one atom just completely gives an electron to another. But other times, in a covalent bond, they're more friendly and decide to share a couple of electrons between them. And this is the key to, well, everything. All the chemistry, all the reactions, it all happens on the outside. There's this quote from our source material that just nails it. The outermost shell is the marketplace where all electron trade takes place. Those outermost electrons, the so-called valence electrons, are the only ones that matter when it comes to chemical reactions. They're the currency of the atomic world. So let's just pause for a second and think about this. We've gone from a tiny, solid ball to a fuzzy cloud that is over 99.9% empty space, which means the chair you're sitting on, your own hand, it's all mostly empty space. So here's the final question to leave you with. Why does anything feel solid? The answer has to do with the powerful repulsion between those electron clouds, a final amazing testament to the strange and wonderful rules of the quantum world.